In this video, we will look at further differentiation techniques that require more than just the basic formula that we have learned. This includes parametric differentiation, implicit differentiation, and logarithmic differentiation. When curves are expressed as parametric equations rather than in Cartesian form, for example, y equals to a function of t, x is another function of t, it is sometimes not possible for us to combine the two equations to get y equals to fx. And thus, it is very difficult for us to differentiate using the standard formula that we have learned earlier. Thus, in this case, it will be much easier if we perform parametric differentiation, which actually just makes use of chain rule. So to do so, we can rewrite dy dx as dy over dt multiplied by dt over dx, where we can easily see that the dt will sort of cancel each other out, and we are thus left with dy over dx. And we can further rewrite this term as dy over dt multiplied by 1 over dx over dt, which is the same as dy over dt divided by dx over dt. Thus, to carry out parametric differentiation, we simply can make use of the formula dy over dx equals to dy over dt divided by dx over dt. For example, if I have the function y equals to et, x equals to sine t, to differentiate this equation, I can do dy over dx equals to dy over dt divided by dx over dt. dy over dt is simply the differentiation of et, which gives me et, divided by dx over dt, which is the differentiation of sine t, and this gives me cosine t. And this term over here will be the differentiation of my parametric equation y equals to et, x equals to sine t. In example 1, we are asked to differentiate the pair of equations that is defined parametrically as y equals to sine t, x equals to t cosine t. And we can leave dy dx in terms of t. That means we can perform parametric differentiation. So let's try to find out what is dy over dt and dx over dt first. So dy over dt will simply be cosine t, and dx over dt will be equals to t multiplied by negative sine t plus 1 multiplied by cosine t, which becomes cosine t minus t sine t. And therefore, dy over dx will be dy over dt, which is cosine t, divided by dx over dt, which is cosine t minus t sine t. And this is the differentiation of our parametric equations. In some equations, it is impossible for us to express y explicitly in terms of x. For example, we might have an equation that looks like this. There is just no way for us to express y in terms of x, for us to carry out direct differentiation to find out dy dx in terms of just x. However, we can carry out implicit differentiation to obtain an expression for dy dx in terms of both x and y. Carrying out implicit differentiation is simply applying the chain rule repeatedly, treating y as an unknown function of x, or y equals to fx. As a simple illustration of how implicit differentiation works, let's revisit the simple formula of differentiating e to the power of fx. Using chain rule, we have learned that differentiating e to the power of fx gives us e to the power of fx times f prime x. Now, if we replace the fx with y, what we will get is differentiating e to the power of y equals to e to the power of y times dy over dx. Now, if we extend this equation into something slightly more complicated, say e to the power of y plus x plus y equals to 0. We can make use of this technique over here to show that dy over dx is equals to negative 1 over 1 plus e to the power of y. But how do we carry out the process to get us from the first equation to the final derivative? This is part of implicit differentiation that we will be illustrating in the next slide. Starting from the original equation, we differentiate both sides with respect to x throughout. We can break up the terms on the left side and differentiate them one by one for clarity. Differentiating ey gives us e to the power of y dy over dx. Differentiating x gives us a 1, and differentiating a y gives us dy over dx. And thus, we obtain this differential equation, which we can now rearrange to express dy dx in terms of x or y or both of them. In example 2, we are asked to differentiate this equation over here and leave our answer for dy dx in terms of x and y. And obviously, it is very difficult for us to express y in terms of x, and thus it will be easier if we just perform implicit differentiation. So let's look at the terms individually. If I were to differentiate y tangent inverse x, this gives me y times 1 over 1 plus x squared plus dy over dx times tangent inverse x. This is going to be equals to, if I differentiate this term over here, e to the power of xy multiplied by 1 times y plus x times dy over dx. So now I have a differential equation in terms of x, y, and dy dx, and I will be able to rearrange to give dy dx in terms of x and y. So let's do a small expansion on the right hand side first. This gives me y e to the power of xy plus x e to the power of xy dy over dx. And I'm now going to bring this term to the left hand side and this term to the right hand side. And therefore, I will have dy over dx multiplied by tangent inverse x minus x e to the power of xy equals to y e to the power of xy minus y over 1 plus x squared. And now you can see that I simply have to divide this term across and I will get an expression for dy dx. So let's proceed to write down the final answer. Dy over dx thus equals to y e to the power of xy minus y over 1 plus x squared divided by tangent inverse x minus x e xy. And this will be the final answer for dy dx in terms of both x and y. In example 3, I'm going to make use of implicit differentiation to show the formula that we have learned earlier. Differentiating sine inverse x equals to 1 over square root 1 minus x squared. So first, I will let y equals to sine inverse x. That means if I find dy dx for this expression, it will be the same as finding out the formula for differentiating of sine inverse x. Okay, I'm going to rewrite this equation as sine y equals to x. Now I can differentiate this equation implicitly. I get cosine y times dy over dx equals to 1, and therefore dy over dx will be equals to 1 over cosine y. But I do not want to stop here because what I need to show is in terms of x, not y. And I can apply the trigo formula sine square y plus cos square y equals to 1 over here. So this I can rewrite to become cos square y equals to 1 minus sine square y, and therefore cos y will be equals to square root 1 minus sine square y. And therefore this dy dx expression can be written as 1 over square root 1 minus sine square y. And note that sine square y is actually sine y square. And sine y, we know it is just x. Therefore, this equation can be changed into square root of 1 minus x squared at the denominator. And this will be the formula for differentiating sine inverse x. From the basic differentiation formula, we have learned that differentiating ex gives ex. But what about differentiating a to the power of x? Also, we have learned that differentiating x power n gives us n times x power n minus 1. But what if we want to differentiate the term x to the power of x? There is no way that we can make use of any of our formula that we have learned to do so. And therefore, as a general rule of thumb, whenever we see x in the power, we can make use of logarithmic differentiation to help us derive the value for dy dx. To perform logarithmic differentiation, we follow 3 steps. Let's take, for example, if we have the equation y equals to x to the power of x, and we want to differentiate it to obtain an expression for dy dx. First, we will take natural logarithm or ln on both sides of the equation. So we will end up with ln y equals to ln x to the power of x. Next, we can make use of the power law of logarithms to bring the power down. So we will end up with ln y equals to x ln x. And the reason for doing so is once we bring the power down, it becomes a product and we can apply product rule. Once this is done, we can perform implicit differentiation on the resulting equation to get dy dx. So from here, we will get 1 over y dy over dx equals to x times 1 over x plus 1 times ln x, which if we rearrange will give us dy over dx equals to y multiplied by 1 plus ln x. And if we are interested in dy dx in terms of just x, I can change y back into x power x, and therefore I have x power x 1 plus ln x. And so these are the 3 steps that we follow if we want to perform logarithmic differentiation when we see x in the powers. In example 4, we are now asked to show this formula over here, where if we differentiate a to the power of x, it will give us a to the power of x multiplied by ln a. So first thing we do is to let y equals to a to the power of x, which means if we want to differentiate a to the power of x, it is the same as finding dy dx for this expression. And now let's perform logarithmic differentiation. Step number 1, I will take ln on both sides. This gives me ln y equals to ln a to the power of x. Next, I can bring the power down, so ln y equals to x ln a. Now I can apply implicit differentiation to get 1 over y dy over dx equals to ln a, and therefore dy over dx equals to y ln a, and again y I can change it into in terms of x, which gives me a to the power of x ln a, which is the same as the formula for differentiating a to the power of x. In example 5, we are asked to differentiate this expression, and we have to perform logarithmic differentiation since there is a variable in the power. So first, we will let y equals to sine x to the power of ex. Next, we will take ln on both sides to get ln y equals to ln sine x to the power of ex. Next, we can apply the power law. So ln y equals to ex times ln of sine x. Now we can perform our product rule and differentiate this term implicitly. And this gives us 1 over y dy over dx equals to ex times cosine x over sine x plus e times ln of sine x. And therefore, dy over dx will be equals to y multiplied by ex cosine x over sine x plus e ln sine x. Again, if I want to express y in terms of x, I can do so very easily. This becomes sine x e to the power of x multiplied by ex cosine x over sine x plus e ln sine x. And that's it.